Hey everyone, in this video I'm going to solve some problems from section 4.6 variation of parameters doing it kind of like Patrick JMT from the videos we watch, the Sharpie and the paper. So here's a 22 y double prime, and this is a 4.6 variation of parameters, plus 4y equals 12x squared minus 6x e to the 2x. So we are going to start with the complementary solution, which is made up like this: yc equals e to the mx, which means yc prime is just n e to the mx. I'm doing this just this time. The other times, for the other problems, I'll skip it. Yc double prime equals n squared e to the mx. So if you plug these in, yc double prime here, yc prime here, yc here, and we set it equal to 0 because it's just the homogeneous part of it. We're going to get m squared e to the mx minus 4 m e to the mx plus 4 e to the mx equals 0. So take out an e to the mx from all of those. M squared minus 4m plus 4 equals 0. I'm just going to divide through by this and cancel that. Now we have m squared minus 4m plus 4 equals 0. Nice little factoring gets us m minus 2 squared equals 0. And so we'll get m equals 2 with multiplicity 2, which is important because now we can construct our complementary solution. So we have y1 equals, this is y1 of the complementary solutions. We'll have y1 equals e to the 2x because we had yc equals e to the mx. We got m equals 2. We get to plug that in here. So yc equals e to the 2x, and then the rule is if we get multiplicity of 2, y2 is just going to be x e to the 2x. And so now when we're forming our complementary solution, we're going to have yc equals c1 e to the 2x plus c2x e to the 2x. And so now we'll move in, that's kind of review. We're going to move into the non-homogeneous part, the variation of parameters part. So draw this to separate it out. And there's two ways to do this. And I'm going to start with the less memorizing way. So in this method, you're going to start with your particular solution is going to have the form yp equals u1 of x, y1 of x, plus u2 of x, y2 of x, which I'm just going to write as u1, y1, plus u2, y2. And with a lot of algebra, we can simplify this down to a lot of algebra, plugging into our original equation and everything. We'll end up with equations for u1 prime. So you get u1 prime equals the w1 or Wronskian 1 over the Wronskian, and u2 prime equals w2 over w. And so I'm going to put this up here and show what all these Wronskians are. So the w is just the Wronskian we're all familiar with, y1, y2, so it'll be y1, y1 prime, y2, y2 prime, and in this case, we actually get, so we have our y1 and y2 here, e to the 2x, so the derivative of that's just 2e to the 2x, and then x e to the 2x. Derivative of this, we're going to use the product rule, derivative of the first times the second. So e to the 2x plus first times the derivative of the second, which would be 2e to the 2x times x, so 2x, e to the 2x. And so now we just evaluate the determinant. So we'll do this cross. First, e to the 2x times e to the 2x plus 2x e to the 2x, writing this below, minus, for the other cross, this will be 2e to the 2x, x e to the 2x. And so now we get, expanding this, we'll get e to the 4x plus 2x e to the 4x, and then for that's this distribution, and then subtracting, well, so we're going to subtract 2x e to the 4x. The exponents add. So these cancel. We're left with, this is just e to the 4x, the w, Wronskian. So now kind of show the basic form of, I'll do the w1 first. So w1 is, we have, it's a determinant as well. We're going to have 0 and then f of x here. And then y2 and y2 prime here. And so I'm not going to plug this stuff in. I'm going to evaluate it and then plug in later just because it'll be less writing. It's a little easier to do it that way for this part. So doing the first cross, we're going to get 0 times y2 prime, which will go to 0. Minus, we're going to do the second one. This is where it gets interesting. y2 times f of x. And I'm just going to write this down here as negative y2 f of x. And so now, looking back here, we have w1 and w, so we can find u1 prime, which can be used to find u. So I will do that next. I'll put this up here as well. And so we know u1 prime equals w1 over w, which is negative y2 f of x, we got that from here, over, and we got e to the 4x when we evaluated the first determinant right here. I'm going to box these because they're both important. You can see them a little easier. And then, so now going back here, we see y2, we got x e to the 2x. So x e to the 2x. And then now f of x, this is just this term. Since it's non-homogeneous, we have the homogeneous part equals the f of x. So I'm going to plug that in here, and I'm going to do 12x squared minus 6x, and then parentheses e to the 2x. Sorry, that's small. E to the 2x. This is all over e to the 4x. So what I first notice is we have e to the 4x, e to the 2x, and e to the 2x. So these would add, and they would add to e to the 4x, the two e to the 2x terms. And then these can just cancel with the ones on the bottom. And so we are left with negative x times 12x minus 6x, which is negative 12x cubed minus, or plus, sorry, because that distribution, plus 6x squared. So that's u1 prime, and so u1 is just the integral of u1 prime dx, which we'll just write negative 12x cubed plus 6x squared dx. It's just evaluating an integral. So negative 3x to the 4th plus 2x cubed. Yes, that is it. And so now when we're forming our particular solution, yp, will be this form, u1, we got the u1 and we had the y1. Now we just need to find the u2. So I'm going to get a new page. We will find, first have to find w2. So we had, so w2 is the determinant with y1 and y1 prime, and then 0 and f of x. So it's just kind of flipped. You keep the, you move the 0 and the f of x part over one column. You can think of it like that from W1, and you leave the, you'll have it replaced with the ones that would be there in the normal Wronskian. So yeah, the first column has the y1 and the y1 prime. And this can expand to more dimensions, which we'll see later in another video. Right, so I'm going to evaluate this one in a similar way to the other one. Y1 f of x, and then minus 0, which is just y1 f of x. And so u2 prime w2 over w, y1 f of x over e to the 4x. And so now we can go back to this, and y1 is e to the 2x right there. So plugging that in, f of x is still 12x squared minus 6x times e to the 2x. And this is all over e to the 4x, so I'm going to cross these guys out again. You can still do that. And so u2 prime equals 12x squared minus 6x, which means u equals, just going to take the integral of this, okay, so this is u2. This is u2, and we got u1 in the previous step. So now we're gonna, actually I can do it right here. Form the particular solution. u1 y1 plus u2 y2. u1 is negative 3x to the 4th plus 2x cubed. y1 was e to the 2x. And then u2 was this one, 4x cubed minus 3x squared, and I'm going to write the multiplication up here, the y2 up there, x e to the 2x. So now distribution gets us negative 3x to the 4th e to the 2x, and then right there, and then plus 2x cubed e to the 2x, and then same thing over here. But we have this x, so we're going to get 4x to the 4th e to the 2x, and then minus 3x cubed e to the 2x. And so we can see this term and this term, they each have x to the 4th e to the 2x terms. So this will become, and it's 4 of them minus 3 of them, so this is x to the 4th e to the 2x. Same thing with these, we get a negative 3x cubed e to the 2x and 2x cubed e to the 2x. So this will be minus x cubed e to the 2x. Sorry for the cramming in there. Let's see. So now we can put those together and get the general solution. So we have y equals, and then we'll have yc. Come on, pens. yc plus yp. And so now we'll have y of x, right? And that would be fancy. yc, remember we got back here c1 e to the 2x plus c2x e to the 2x. yp we had right here, and like that. And that, so we'll add that on, plus x to the 4th e to the 2x. And now we have our solution. There we go. Okay, here's one last problem from section 4.6, variation of parameters in the textbook. This one is number 30, and it has it's a y triple prime plus y prime equals tangent of x, which means we're gonna have three three functions in the complementary solution. So we'll have c1, we'll end up with c1y1 plus c2y2 plus c3y3. Similarly, when we're making the particular solution, which is important for variation of parameters, we're going to have u1y1 plus u2y2 plus u3y3. So I'm going to start with that complementary solution. So I'm just going to turn this into m cubed plus m. So this is the auxiliary equation, augs eq. M cubed plus m equals 0, which becomes, we can take an m out of each, m squared plus 1 equals 0. So we end up with m equals 0, m squared plus 1 equals 0. And so for this part, for the m squared plus 1 part, we'll end up with, we'll get m squared equals -1, so m equals positive negative I. And so the complex root with the form of alpha plus beta I, we can see that alpha is 0, beta equals 1. So now when we're making the complementary solution, we have we'll do c1 cosine of x. So cosine of x, because it would be cosine of beta x, and beta is 1. And there's an e to the alpha x in front. Alpha is 0, so that's just 1. And then plus c2 sine of x plus c3. The c3 is there because if m equals 0, then this is actually, I should write this out. It would be e to the mx, which is e to the 0x, which is 1. 1 times the constant is c3. So here's our complementary solution. And on top of that, I'm just going to write I'm going to split these up. So y1 is cosine x, y2 is sine x, y3 is 1. And so now we're going to, so when we're doing these, we have to use that Wronskian way. So we're gonna make four Wronskians, and they'll be the W, W1, W2, and W3. So our particular solution is gonna look like this: YP equals U1 Y1 plus U2 Y2 plus U3 Y3. And each of these is each U term is gonna have the form as follows: U1 prime equals W1 over W, U2 prime equals W2 over W, U3 prime equals W3 over W. So we're gonna start with just W. So this one's gonna be a little bigger. We're gonna have Y1, Y2, and Y3. So this has to be a square matrix, so we're going to be taking the first derivative and the second derivative, so of each of these. So we have y1 prime and y1 double prime, so y2 prime, y2 double prime, y3 prime, y3 double prime. And so now we have to evaluate, actually hold on, I'm going to plug in we're going to plug in our values from up here. So cosine of x, so cosine prime is negative sine, and then the derivative of negative sine is negative cosine. Y2, right here, sine of x, derivative of this cosine of x, derivative of that negative sine of x, and then 1, derivative of that 0, and 0. So now we will evaluate this. So I'm going to use the way you bring the top left one out, then evaluate the determinant of these 4. So we're taking those 4 out. And then for the next part, sine of x with these 2 and these 2. And we subtract because it's the second part of the determinant, which will get us negative sine of x, negative cosine of x, 0 and 0. And then finally we're going to add the last one, which is this one, then determinant of these four. Okay. This paper gets more colorful as we go. Now let's simplify. Cosine of x, and when we evaluate this one, I'm going to do the x method. So cosine of x times 0, 0, sine of x times 0, negative sine of x times 0, 0. I'm just going to write this times 0. Minus sine of x. Sine of x is in front. Do the same thing. We get 0 for both of these. Plus 1. So now we'll have a negative sine x times negative sine x, so sine squared x, minus negative cosine x times cosine x, plus cosine squared of x. We know this just goes to 1, so I'm going to write w equals 1. We have the Wronskian, general Wronskian. Now I'll show you guys how to get W1 and W2 and W3. So it looks similar to what we did before. I'm going to change colors here. So, come on. Here we go. W1. So we're going to have 0, 0, f of x, and then we're going to replace it with stuff from here. We're replacing the first column first with 0, 0, f of x, and then we just fill in the rest. y2, y2 prime, y2 double prime, y3, y3 prime, y3 double prime. And now when we plug everything in, okay, so f of x, we're going to get that from here. So we have the homogeneous part equals the f of x. And so f of x will be tan x here. I'll plug all this in here. 0, 0, tan of x. And then these I'm just going to fill up with this part of the Wronskian that we had up here, because they're identical. Now we are going to evaluate this one in the same way we evaluated the last one. So we're going to have 0 times this determinant. And so we see these both go to 0. The first two go to 0 because in this one we have oh, never mind. Okay, sorry. This first one goes to 0 because it's multiplied by 0. The second one is negative sine times, so 0 minus 0 is 0. Sine of x times 0. So this is just 0. And then this part, we have 1 times, and so then we're going to take this determinant and 0 times negative sine x, 0, minus tan x cosine x. So since tangent is sine over cosine, the cosines cancel. We're left with negative sine of x. So I'm going to write this down here. W1 equals negative sine of x. We'll use that later. So we have w equals 1, w1 equals negative sine x. Now, let's switch to orange for w2. And so now, like we had here with column of 0, 0, and then f of x at the last term, we're going to move that one over and then fill the first one back with the y1 terms. And let me check to see if, okay, back oriented. Almost knocked my setup over. Let's get back to the problem here. And I'm just going to fill these up with values from the original Wronskian again. So cosine x, negative sine x, negative cosine x. And now in this column, we're going to have the 0, 0 f of x. In the last column, we're going to have 0. Oh, sorry. 1, 0, 0. Because that was the y3 part. So now we're going to evaluate this. And this part we're going to have. And for the final term, 1, negative sine of x, negative cosine of x, 0, tangent of x. And when we evaluate this, it goes to 0 because these multiplied together are 0, these multiplied together are 0. Similarly, these multiplied together are 0, and these are multiplied together are 0, and we have 0 in the front. So we end up with 1 times this determinant on the far side. I'm going to cross these out. Boom, boom. And this would be negative sine tan x times 0, or minus negative cosine x times 0, which is 0. So this is what we get in the end. We can rewrite this as the following. This will come to negative sine squared of x over cosine of x, because tangent x is sine x over cosine x. And negative sine squared x is the same thing as 1. It's the same thing as a negative 1 plus cosine squared of x, because if you add a sine squared of x to each side and then add a 1 to each side, you get sine squared x plus cosine squared x equals 1. This is all still over cosine of x. And so now when we separate this into two terms, we get negative secant of x plus cosine of x. And that is W2. So far we have W equals 1, W1 equals negative sine x, and W2 equals negative secant x plus cosine x. Finally, we will evaluate W3, which will be done in black. Yes, let's do it. Following the same pattern we had before. Sorry, this is y2. This is y2 prime. Oh, sorry. Get the video back on track. There we go. And, oh shoot, what was I thinking? I wasn't thinking. Sorry. Last column is 0, 0, and then f of x. Sorry about that. Let's rewrite this. Let's plug in our information. We know that the original, so it's cosine, oh yes, okay. And so this will be 0, 0, and tangent of x. Time to evaluate. And since we have a 0 in front, I'm not going to write out the last determinant because it's 0 times the determinant of these 4, and 0 times anything is 0. Cosine x times tangent x is sine of x. And this is 0. Finally, negative sine x, and then we have negative sine x times tangent x, which will be, we end up with, I'm going to just write it as what we had up here. And this part, and this part of it evaluates to 0. What did I write here? Sorry, this should be multiplication. This is multiplication. Negative sine of x times, and then negative sine x, tangent x, which is negative sine squared x over cosine x. And this part comes to 0, so I'm not going to write that part out. And so from here, we can do some simplifying. Let me rewrite this. First thing I'm going to do is take a sine out of everything. So we'll get sine of x times cosine x plus sine squared x over cosine. And now we're going to, so we want to get a common denominator on the inside, which will be, so we have to multiply this cosine x term by cosine x over cosine x. And so then we get cosine squared of x on the top. We can add that to the top. We can divide that all by cosine x. And since this goes to 1, what's on the inside ends up as, which sine of x over cosine x is tan of x. So we can see that W3 equals tangent x. So going back, we have W equals 1. W1 equals negative sine x. W2 equals negative secant x plus cosine x. W3 equals tangent x. So now it's time to plug in to these formulas. They're similar to what we had before. Let's do it like this. U1 prime equals W1 over W. And I'm going to plug, oh, actually, hold on a second. Before I do this, I'm going to rewrite all of our Wronskians that we had on one page. So, see that right here. W equals 1. W2, oh, sorry. W1 equals negative sine of x. W1 negative sine of x. W2, that's right here, negative secant x plus cosine x. And then W3, tangent x. Now we can start solving for our u terms. u1 prime equals w1 over w. And I'm just going to do it all here. Negative sine of x over 1 equals negative sine of x. u1 equals the integral of u1 prime dx. Cosine. So the u1 equals cosine of x. Now I'll switch colors for u2. Since w is 1, I'm just going to, so this is u2 prime equals w2, which equals negative secant x plus cosine of x. So u2, a little error there. So therefore u2 equals the integral of negative secant x plus cosine x dx. Integral of negative secant is negative natural log of secant x plus tangent x of the absolute value of secant x plus tangent x, and then the integral of cosine of x is sine of x. That is that, and let's move on to u3. u3 prime equals w3 over w. We found w3 to be tangent x. So u3 integral of tangent x. And we don't have constants because this is a particular solution, and only the general solution, or only the complementary solution has constants of integration. And the integral of tangent x is negative log natural of the absolute value of cosine of x. Now we can make our particular solution. Remember, we said yp equals u1 y1 like that, and from all the way back we figured out y1 is cosine x, y2 is sine x, and y3 was 1. So u1 times y1 plus u2, and for u2 we got negative log natural secant x plus tangent x plus sine of x, and this was all, we multiply this by the y2, which is, in this case, sine of x. I'll write it sideways so it fits. Finally, we add this to u3, negative ln cosine of the absolute value of x, and we multiply this by y1, y3, which is just 1, so I'm going to leave it like that. And so when we simplify this, we'll get cosine squared of x. And when we do the distribution here, we get a sine squared of x, kind of doing it backwards, minus sine of x ln secant x plus tangent x, and finally we'll add on the last term. And so cosine squared x plus sine squared x is 1, and that won't be included when we add our particular solution to our complementary solution, because our complementary solution had C3 on the end, which takes in any constants, kind of absorbs it, is how I think of it. And let's illustrate this. Y of x equals yc plus yp. So our complementary solution, remember, it was c1 cosine x plus c2 sine of x plus c3. And we're going to be adding on yp. And so this part of yp just goes to 1, like I was saying. And 1, we can just add that into c3 and redefine c3 as including that 1. So we don't have this cosine squared x plus sine squared x part that we're going to add on, but we do add the rest. And I'll put it in green. Minus sine of x ln secant x plus tangent x minus that ln absolute value cosine x term. So that is the general solution to, let's see, to number 30, y triple prime plus y prime equals tangent x. Ooh. I think these three constant of integration problems are pretty fun. So there we go. Hello. In this video, I'm gonna do one question from 4.9, which is the systems of linear differential equations. And so I got this one from the textbook, and it's gonna be number 14, which is the system is made up of dx by dt plus dy by dt equals e to the t. The other equation is negative d2y by dx2 plus dx by dy, d2x, negative d2x by dt2, and then dx plus dx by dt plus x plus y equals 0. First step is to convert these into their forms with the differential operator. So dy, or dx, this is dx plus dy equals e to the t. The other one becomes negative d squared of x plus d of x plus x plus y equals 0. And I'm going to simplify this further into, let's see here, I'm going to rewrite the top one. And then the bottom one, we can combine all these, the coefficients, or sort of coefficients, the differential operator for each part of x. So in the parentheses, we'll have negative d squared, and this is negative d squared, plus d plus 1, coefficient here is 1, x, and we're adding y, and we get 0. So now we're going to eliminate, and I'm going to multiply the top equation by this differential operator, but I'm going to multiply that differential operator by negative 1, and so that we can eliminate them. So we get d squared, because negative d squared times negative 1, d squared, minus d minus 1. And we still have this d in front of the x. And then we do the same thing for y. And also for e to the t. Okay. And I'm just gonna bring, oh, and so now on the bottom, we're gonna need, I'm gonna eliminate the x, all the x and all of its derivatives first. And so I already multiplied the top by what's in front of the x on the bottom, and now I've multiplied what's on the bottom by the coefficient, or by the operator of x on the top. So this one's d, so now I'm gonna do d times and then negative d squared. This is carrying over from here. And then we are gonna add the differential operator in front of the y. And in front of the 0, it's just 0. So I'm gonna make it equal to 0. Still a 0. Now let's simplify. So the x terms cancel because we have d squared minus d minus 1 all times d, and then d times negative d squared plus d plus 1. So everything with the x cancels, which is what we were going for. Now we can simplify what we have in front of the y. So on the top equation, it will be d cubed, because distribution, and then if we, since the derivative of e to the t however many times is just e to the t, this is going to be e to the t minus e to the t minus e to the t, which ends up being negative e to the t. And then on the bottom, we're left with just dy. So now we can combine these two equations. So I'm going to do it like this. We'll get d cubed minus d squared y equals negative e to the t. Okay. Now we need we're going to solve this part now. We need this equation. We need the auxiliary equation, which in this case is m cubed minus m squared. It's easy to see because we factored out the differential operators. And it equals 0 because we're just looking for the complementary solution now. So factor this, m squared times m minus 1 equals 0. Yes, from this we can get this. And now when we solve for m, we get m equals 2 with multiplicity 2. And m equals 1. Great. The rule when we have, this is m equals 0. M equals 0 because m squared equals 0. We solve that, we get m equals 0. Yes. And the rule here is that when we're constructing our complementary solution, we're going to have yc equals c1 e to the 0t plus c2 t e to the 0t plus c3 e to the t, and e to the 0t is 1. So yc equals c1 plus c2t plus c3 e to the t. There's our complementary solution for y. Now I'm going to use the guessing method for finding the particular solution. And so my guess, looking over here, I see negative e to the t. So my first guess is yp equals a e to the t. But when I look in here, I see we already have a constant e to the t term. So I know this isn't going to work when I plug it in. So I multiply this by t. So yp is actually going to be a t e to the t. Now we're going to be plugging this into this part of the equation for y. So we're going to need the triple derivative of y. So just start with of yp. I'll start over here. For the big reveal, yp triple prime. And I'm doing this in the order of derivative of the first. So I did this for all these. Derivative of the first times the second, so a, which is the constant. Derivative of the first is 1 times e to the t, plus derivative of the second times the first, so plus derivative of e to the t is e to the t times the first. I did that for all of them. We can see we get some nice combining of like terms for each of these expansions. And finally, we'll be left with 3a e to the t plus a t e to the t. Excellent. Now we plug these into this equation. So when we have d cubed minus d squared y, this is the same thing as y triple prime minus y double prime. So we're going to have this part minus this part. And it is going to equal whatever we have at the end here because we're looking for the non-homogeneous part of this equation. Canceling, so this will cancel with this because we have the negative sign. And this will reduce to a e to the t equals negative e to the t. Therefore, a equals negative 1. From this, we can construct, so now we have yp equals, so we can plug this negative 1 in here. We're going to get yp equals negative t e to the t. That's our particular solution for y. Finally, I will write our general solution for y. Oh shoot, it's colored. Let's get the colors in here. There's our general solution for y. Now we can move on to solving for x. I'm going to rewrite my equations one more time so we can see them and work with them. Sorry. We had a simplified version. Negative d squared plus d plus 1. About that. Let me write it one more time. Now we can start to manipulate these in order to eliminate y. In the previous example, the previous time we did this, we eliminated the x's. So we're going to be eliminating y here. And let's start by, the only thing that's different about the y's is on the top we have a differential operator in front, and the bottom we don't. So I'm going to multiply the bottom, the whole thing through, by the negative differential operator so that when we add them together we get 0. And so this leaves the top unchanged. The bottom, however, we're going to add differential operator and then the other differential operator. Sorry, we're going to add negative differential operators because we want to get rid of y. We do not want it to add that. And I just left 0 here because derivative of 0 is 0. And negative derivative of 0 is also 0. Let's simplify one more time. This is just transferring over. And this part, a little distribution, will get us because these factors cancel. Sorry. This canceled too. That wasn't part of it. So now I'm going to combine the equations, and we can see the dx part. We have a dx on the top and negative dx on the bottom. They're going to get canceled. Sorry, yeah, these are being added together. So we get an e to the t. It all equals e to the t. Now let's find the, now we've got to find the general solution for x. And we'll start with the complementary solution, like normal. And if we look at this, we're gonna see d cubed minus d squared. Wow, this looks really familiar. So since this part of the equation is the same for the x and for the y, d cubed minus d squared operating on y or operating on x, since they're the same, we're going to end up with the same complementary solution, c1 plus c2 t plus c3 e to the t. However, because this is with our x, we are going to need different constants, which we'll have to find the relationship between them later. That's the last step, so I'm going to write that. C4 plus C5t plus C6 e to the t. Finally, I'm going to form a particular solution, and it'll be, this is xc. Now we'll have a xp, which it's going to also be at e to the t, because we examine this, we see it's e to the t, we know we have an e to the t term already, so we're going to put a t in front of it, and we're going to get the same result. When we differentiate this 3 times, we're going to get the same result as what we did for y triple prime of p and for y double prime of p, which means when we combine them, we're just going to end up with, when we combine them all, we're going to get a e to the t equals, in this part, or sorry, this part of the equation, and it'll equal e to the t, which means a just equals 1. So now we can make our general solution for x pretty easily. And it'll just be c4 plus c5t plus c6 e to the t plus this t e to the t term on the end. And now we have to find the relationship between all the terms in this equation. So I'll put this kind of like this, Let's see if we can still see the important parts. Oh, never mind. They're both on this sheet of paper. Great. So, yes, we have both y, oh, I just realized this, sorry, y of t, this is y of t, and up here, and x of t down here. We are going to now plug in these to the different differential equations, and we're going to figure out, so we're allocated, we get 3 coefficients because this equation is second order in x. I'll go back to that sheet. Second order in x, d2x by dt2. And first order in y, the highest derivative we get for y is just dy dt. So we get 2 constants for the x part, 1 for the y part, but they're combined. We get 3 total. We get 3 total coefficients. And if we look at our equation, for x of t, we have 3. And for y of t, we also have 3. So we're going to need to rewrite 3 of these in terms of the other 3. And this is where we plug in to the other equation. So I'm going to, we're going to use the first one, dx dt plus dy dt equals e to the t, which is, it can also be written like this, x prime of t plus y prime of t equals e to the t. And when we're solving for x, so we have our x here, so this means x prime of t is going to equal, it's going to equal c5, because, so when we differentiate c4, we get 0, differentiate c5t, we get c5, differentiate c6 e to the t, we're going to get c6 e to the t, differentiate this, the last part, we'll get e to the t plus t e to the t. When we do the same thing with y prime of t, this will be c2, well, the derivative of c1 is 0. Derivative of c2t, c2. Derivative of c3 e to the t. And, sorry, this is t e to the t. T e to the t, right there. So now we'll have negative e to the t minus t e to the t. Now we're going to add these up and equate it to e to the t. So let's see here. I'm going to, first of all, we can eliminate, so since we're going to be adding these, I'm going to eliminate all of the terms that are the same. E to the t is the same as e to the t, negative e to the t. So, or e to the t minus e to the t is 0. T e to the t minus t e to the t is 0. And now I'm going to group these. So we're going to get I'm grouping them into if they're what they're a coefficient of. I guess each of these is a coefficient of something. So this is so C2 and C5, they're coefficients of x to the 0. I'm just going to leave it as just C2 plus C5. C3 and C6 are both coefficients to e to the t, so I can do C3 plus C6 e to the t, and then it's all going to equal e to the t. Since there's no term for x to the 0 power, on the right side, we can say C2 plus C5 equals 0. I like to, so now we have, we can write one of these in terms of the other. I like to write them all in terms of 1, 2, and 3 because it's cool. And so we'll write C5 equals negative C2. Now we've eliminated one of these. We've eliminated one of those extra constants, and we still have two more. But we'll get the other one over here. So C3 plus C6, we know these have to add up to 1 because the coefficient of e to the t on the right side is 1. The coefficient of e to the t on this side is C3 plus C6. So C3 plus C6 equals 1. Again, I'm going to write C6 in terms of C3. So C6 equals 1 minus C3. And notice we are still missing. We still need some more. We still need to do a little more work. I'm going to now calculate x double prime of t, and we will use this. Excuse me. We will use this to find to plug into the second equation we had above, negative d2x by dt2 plus dx by dt plus x plus y equals 0. And so we have x prime of t up here. I crossed stuff out because I was canceling with y prime of t, but that's not the case here. So x double prime of t, so derivative of c5 is 0. Derivative of c6 e to the t, c6 e to the t. Derivative of e to the t plus t e to the t, well, when we do that expansion, we will find that this is 2 e to the t plus t e to the t. And, which is convenient. We can okay, so now I'm going to write the equation that we're plugging into for convenience, and I'm going to write it in terms of, in this way. Plus x prime of t plus x of t plus y of t equals 0. Now I'm going to plug in everything I know. I know this is c, so we're going to distribute the negative sign to everything in front of x double prime of t. We'll get negative c6 e to the t, or negative c6 e to the t minus 2 e to the t minus t e to the t. X prime of t. This is c5 plus c6, that term. But we're going to have a 2 in front of each term for this time around. So plus 2c5 plus 2c6 e to the t plus 2 e to the t minus, plus 2t e to the t. Now we add on just x, which we have in this paper, which I'll put, this is plus c4 plus c5t plus c6 e to the t plus t e to the t, and on top of that we are going to add y, and I'll put y in this color, and we found y to be up here, c1 plus c2 plus c1 plus c2t plus c3 e to the t minus t e to the t. And this whole thing is equal to 0. Now I'm going to look for terms that I can eliminate. So it's negative c6 e to the t and a positive c6 e to the t. These can get canceled. Negative 2 e to the t, positive 2 e to the t. These cancel. Negative t e to the t, positive t e to the t. Cancel. And from here we can construct the last few relationships that we need in order to find, I'm just checking my notes here, making sure I got this all correct. I just realized I made a mistake. and when I was plugging these in. So allow me to eliminate everything I have here. Sorry about that. I'll leave a note there to skip over. Okay. Sorry, I made a mistake here. I'm fixing it now. Let's plug into this equation. So we have our x double prime of t here. And we're going to make sure everything has a negative sign in front of it. Negative c6 e to the t minus 2 e to the t minus t e to the t. Now we're going to add x prime. We have that up here. And finally we're going to add x, which is right here. And then finally, on top of that, we're going to add our y, which is up here. Now I will cancel terms. Negative c6 e to the t, we can cancel this with this c6 e to the t. Negative 2e to the t, here's an e to the t. Oh, and this whole thing's going to equal 0 because we're plugging into this equation. Negative t e to the t can cancel with this t e to the t. And then this t e to the t can cancel with this one. And that's all the eliminating we can do. But we can rewrite in terms of what each of these is a coefficient of exactly. So I'll start with the just constants. So in this one, we're going to have c1. So c1 doesn't, it's not multiple, it's c1t to the 0. So c1 plus, and then we have a c4. And then we have a c5 up here. And I'm going to put these into parentheses to kind of group them, and then just cross these off. So we don't have to worry about those anymore. Now let's do the terms with a power of, or with e to the t. And so I'm going to take this negative 2 e to the t and this positive e to the t, so those will combine into negative e to the t on this side, which is the same thing as equaling e to the t on the right side. So I'm going to write this equals e to the t and cross these two out. Dealt with those. Now I'm going to write what we have for the t. What are the constants for t? We have a c5 here and a c2 here. No, nothing else. So we can say c2 plus c5t. And now I'm going to finally add what we have for, and these can get canceled. c2t, c5t. Now I'm going to add what we have for the coefficients of e to the t. And in this one I'll use this color, and we have a c3 and a c6. So I'm going to again put it in parentheses for grouping. Now we see this equation we've already made up here. c3 plus c6 equals 1. We've already done that. I'm not going to worry about this. And similarly with c2 and c5, we've already done that. It's a good sign. It means we did our work right. This is our new equation, and this is the one that will get us through this problem. And I'm going to write c4 in terms of the other, additionally, this is being multiplied by t to the 0 power. There's no t to the 0 power term on the other side, which means all of these are going to sum to 0. And so we'll have c1 plus c4 plus c5 equals 0. We're going to solve for c4 because we already know c5. and C1, we're okay with taking C4 in terms of that. So we'll get C4 equals negative C5 minus C1, and we know C5 is negative C2, which means this is going to be negative times a negative C2 is a C2 minus C1. Now we have C4 in terms of C1 and C2, C5 in terms of C2, and C6 in terms of C3. We're golden. We can plug these in to the equations we got for x of t, and we'll also have y of t. So I'm gonna put these over here. Grab the paper, and let's get our final answers. So x of t. So we have x of t. We have C4 plus C5, or C4, which was C2 minus C1. So plus C5t we got from, and I'm getting that from here. So we got C5 to be negative C2. So we can put a minus C2t, and then C6 we found was equal to 1 minus C3 right there, which I'm going to plug in here. 1 minus C3. And this is e to the t. And we have a plus t, 3 to the t term. And y was already in terms of C1, C2, and C3, so y of t equals C1. I'm copying this down from the top. And this is our solution to the differential equation. You can, if you found C1, C2, and C3 in terms of C4, C5, and C6, that's fine. If you had 1, 2, and 3 as, if you solve for x first, you're going to have the constants, they'll be flipped as well, but it all means the same thing, same answer. Thanks for watching. Hello, in this video I'm going to solve the hardest differential equation problem I've done in my entire life. And this is number 18 from section 4.9, which is systems of linear differential equations. And let's have some fun. So the equation is dx plus, I'm going to leave some space, we'll see why later, plus z equals e to the t. And so this is, spoiler alert, 3 variable system of differential equations in x, y, and z. So for the next equation, we have d minus 1 x plus dy plus dz equals 0. And for the last equation, x plus 2y plus dz equals e to the t. And first things first, I'm going to eliminate my z terms. It's the easiest one to eliminate. And I'm going to do this by, I notice we have a dz and dz here, so when we add all 3 up, we're going to have a z and then a 2dz term. So I know if I multiply the top through by the negative 2 times the differential operator, and then add it to these 2dz's that we already have, it's gonna go to 0. So when I rewrite x, or when I rewrite the first equation, it'll be negative d, it'll be negative 2d times d, negative 2d times the differential operator that was already there for x, plus, and then negative 2d times z equals, and we still have this negative. We're going to have to do it in front of the e to the t as well. Negative 2d e to the 2t. The second equation and third equation stay the same, so I'll rewrite those. And so we're going to cancel our z's, boom, boom, boom. When we combine our x terms, we have a negative 2d squared, a dx, a negative x, and an x. So the negative x and the x are going to cancel. This leaves us with our first equation, negative 2d, so it'll be like this. Negative 2d squared plus d of x. And then for y's, we have a dy and a 2y, so when we can combine those, we can put those together. D plus 2y. And then it'll equal, well, if you take the derivative of e to the t, we get e to the t, and we multiply that by negative 2, we get negative 2. Negative 2 e to the t plus e to the t is just negative e to the t. And that's our first equation. So when now we have an equation with an x and a y. Now I'm going to eliminate y. So there's many ways you can do this, and I'm going through it the way I solved it initially, so my thought process. So I noticed z was really easy to eliminate first. That's why I eliminated it first. I noticed this equation didn't help me. I can't really plug this in anywhere and suddenly get an equation that is only in terms of one variable. So instead I went through these and I sought to eliminate y from both of these. And I'll go through how that went. Our first step, I'm going to separate out here. And we have, I'll rewrite. Actually, I'm not going to rewrite. So yeah, the top we leave because it doesn't have y, so we don't have to worry about it. Dx plus z equals e to the t. Second one, I'm going to multiply this through by here we are, yes. I'm going to multiply this one through by negative 2, this equation through by negative 2, this equation through by d, and that will get a negative 2 dy here and a 2 dy here, which will be able to cancel out later. And so that'll look like this. And since it equals 0, it doesn't matter if I multiply by negative 2, it's still going to equal 0. Now, I will do the same thing with the bottom, except we're going to multiply through by the differential operator d. And that gets us and d times, and then 2 and times y. Finally, So we got the d multiplied, and we already had a differential operator there. And so now I'm just going to leave e to the t as e to the t, because when we take the derivative of itself, when we take derivative of e to the t, we get e to the t. Great. Now I notice, yeah, I set this up to eliminate y, and shocker, we can eliminate y. Now let's combine our terms, and I'm going to rewrite each equation. So top one doesn't change. Plus z equals e to the t. Second one changes. We notice this is going to be negative 2d plus 2x plus negative 2d z equals 0. And bottom will be dx plus d squared z equals e to the t. Now we can combine these. And so I notice we have dx, and then negative 2 dx. So those will all cancel, and we'll be left with just 2x. So I'll do this again. They're all leading into this equation, 2 times x. However, we have a d squared here, negative 2d here, and a 1 in front of each z. So when we combine those, we get d squared minus 2d plus 1 z. When we combine the e to the t's, we get e to the 2t. Now we have, this equation's a little more useful. There's a few ways we can do this, but we can combine it with this one to eliminate an x or a z, depending on where we want to go with this. Sorry about that. Okay. And for this next step, I am going to eliminate, so I'm going to take these two equations and eliminate x, the x terms. So I'll rewrite in this color. The bottom one is and this is not e to the 2t. This is 2e to the t. 2e to the t. I want to eliminate x, so I'm going to multiply the top through by negative 2 and the bottom through by d, and that we'll see that can eliminate, that'll eliminate everything in front of the x. And I'm going to just write this as negative 2dx plus negative 2z equals negative 2e to the t. The bottom, we're going to have 2dx, and then we're going to have this term, everything just gets multiplied by d. And when we take the derivative of 2e to the t, we just are left with 2e to the t. Now, we're going to combine these. We notice e to the t terms cancel, and so do these. We are left with d cubed minus 2d squared plus d minus 2z. This is z, these are z, yeah. And that'll all equal 0. So this is nice. We have a homogeneous equation here. We don't have to solve for the particular solution for z. And so in this next step, I'm gonna, we can still do the auxiliary equation. And since we have the d's all factored out, this is just going to be m cubed minus 2m squared plus m minus 2 equals 0. And what I notice is when we can take an m squared out of the first two terms. So this will be m minus 2, and then I'm going to factor a 1 out of each of the next two terms, m minus 2. And from this we can see that we can write m squared plus 1 times m minus 2, since these are just coefficients of m minus 2. Now we can solve for m's here. From this we're going to get m equals positive negative I, and it equals 2. So since we have positive negative I, I'm just going to write a little thing up here. We get alpha equals 0 and beta equals 1. Now when we are writing our complementary solution, it'll be yc equals c1, I apologize, this is zc. zc equals c1 cosine of t plus c2 sine of t plus c3 e to the 2t. Great. Next step is we are going to use this equation that has, hold on, we're going to use this equation that we found with x's and y's, and this equation that only has x's and z's, and then plug it into, we're going to isolate x's in each of them, so we're going to have y, some operators in front of y equals something in terms of x. Similarly, we're going to have some operators in front of z equals something plus something in terms of x. And from that, we can plug into this equation. We can make sure the whatever's in front of this y is the same thing that's in front of this y, and then we can plug in something just in terms of x. Same thing with z, and that will get rid of y and z. We'll just have x, and from that we can find a lot more. We can find some more solutions. We can find our solution for, what am I saying? We can find our solution for x. First step. We take our equations, and in this case, we'll have negative 2d squared plus d x. That's, I'm just rewriting here. And the second one. First step, I'm gonna just leave y on this side, which means adding 2d squared plus x, or minus x, to both sides. Same thing over here. C equals e to the t minus d operating on x. Now we have to manipulate these so that what's in front of this y matches what's in front of this y right there. And what's in front of this y. So whatever's in front of this y has to match that y, and then whatever's in front of this z has to match that z. And I'll write, I'm not gonna write that down. we first notice when we take that equation that has x, y, and z, we'll multiply through by d plus 2 because this part has a d plus 2 in front of the y, and there's no d plus 2 operating on the y in that equation that we're going to be plugging into. And that one will be, it'll be, when we get that d plus 2, it'll look like this. And this is what we get when we multiply through by d plus 2. And so now now we have a 2 times d plus 2y term. We need a 2 in front of this one so that it'll match up. And so I'm going to multiply this equation through by 2. We'll get, I'm going to just factor it in, 2d plus 4y equals 4d squared minus 2d x minus 2e to the t. Great. And so we can see that we've multiplied through and set it up so that we have something in terms of y equals this, and we can plug that right in here. Now we have to do the same thing for z. So what's in front of the z here is a d and a d plus 2. So I'm going to plug those in to what we have for z above, up here. And so that'll be d squared plus 2d Now we have enough to plug into this blue equation. And for the sake of understanding, I'm going to do some color coding here. D plus 2x. And then our 2d plus 4y term we found right here. And our d squared plus 2dz term will fit in nicely here. And this is minus everything in front of x. So I'm going to write it as plus negative d cubed minus 2d squared. And since the derivative of e to the t is itself, d plus 2 e to the t is 3 e to the t. Alright, now we have an equation with just x's and t's, which is really nice. We can solve this. First step is to simplify everything as much as possible. And what we're going to find is, let's rewrite in orange with everything with all of the differential operators in front of that x. So we have a negative d cubed, starting from the highest power here. Get that out of here. Minus 2d squared. Get this out of here. Plus 4d squared. Get that out of here. Plus d squared. And we have a plus 2d and a minus 2d. all operating on x. Oh, sorry, just noticed two more. We also have another d here, plus d, plus 2, all operating on x. Now, never mind. I made a mistake. It was right here. We can't add e to the t terms to the x operating on x. Let me redo this. Negative d cubed, that's front of an x, minus 2d squared, that works too. Plus 4d squared, minus 2d. We can't use these, however, we can use these. That's all operating on x. As far as e to the t terms, so, sorry, these shouldn't be eliminated. D squared plus 2d e to the t. So d squared e to the t, that's e to the t. 2d e to the t is 2e to the t. So this goes to 3e to the t. This is negative 2e to the t, so we're just left with e to the t here. We can subtract e to the t from both sides, and we get 2e to the t. That's what will be on the right. Which, and now we can do some simplifying. We will find negative d cubed plus 2d squared minus d plus 2 times x equals 2e to the t. And this looks familiar, and it's familiar because we did the same thing for y. I'm gonna multiply this all through by -1 now, so it really looks similar. D cubed plus d minus 2 times x. So this is the same as what we did with z. We just found z. And it all equals negative 2e to the t. Notice last time for z it all equaled 0. It was set equal to 0. Here it's set equal to negative 2e to the t. We're going to have to find that particular solution. But as far as this goes, we can use the same problem solving. We'll get c1, we'll get a constant times cosine t plus a constant times sine of t plus another constant times e to the 2t. I'm not going to show that work because it's the same exact work that we just did. So that's how we get xc. And for these, I will call it c4 because we're just going in order. And then now we have to find that particular solution. And I'm going to say yp equals a e to the t. And what's cool about this is it's the same thing as yp prime and yp double prime and yp triple prime. When we plug these, no, these are x's, xp, sorry about that, xp, a e to the t, it's xp prime, xp double prime, and xp triple prime. When we plug these all in, we'll have I'm going to plug them in here and set it equal to that. This is how we use the guessing method. You notice we'll end up with negative 2a e to the t equals negative 2 e to the t. So a equals 1, which means yp just equals e, sorry, this is xp. xp equals e to the t. Now we have our general solution of x. I'm just going to write it in orange. And it's xc plus xp, so so far we have zc, or zc, which is just z, because there is no particular solution, and x. Okay, now it's time to look for our solution for y. we're going to start by manipulating some of those original equations. I will start with the first equation I'm going to make is going to involve all three of our original differential equations, and I'm going to eliminate x from each of them so that I can get a term with just, I'm going to eliminate x, make an equation with just y's and z's, and then from there we can put that, we can write an equation for z in terms of y, and we already have one for x in terms of y over here. We can rewrite this to have x in terms of y. Then we can plug that into either one of those original equations to replace x's with z's and then replace, or x's with y's and then replace z's with y's as well. And then from there we can solve for z. So I'm going to start by just listing out each equation, and let's see, okay. So this is dx plus z equals e to the t. Next one. So I'm writing them in different colors because there are a lot of them here, or there are three, and they really, it can get confusing. It can get very confusing. You can write down everything, have all your answers, have all your work making sense in your head, but when you look back on it to study for a problem, it can just look like complete nonsense. I want to eliminate x, and what I notice is if I multiply the top equation through by -2, I'll get -2d. If I multiply this one through by 2, I'll get positive 2d minus 2. Then if I multiply the bottom one through by 2, I'll have a positive 2. And so this will be, the positive 2x will cancel with this negative 2x, the positive 2d will cancel with this negative 2d. So let's implement this. And so I got -2 multiplied by each term on the top, and now I'm going to multiply the second equation through by 2. 2 and this one equals 0. Equals 0. There we go. 0 times 0 is 0, so I'm going to leave it as 0. Or 0 times 2 is 0, so I'm leaving it as 0. Finally, the bottom one also gets multiplied through by 2. So yeah, d minus 1. Okay, so 2 times x plus 2 times y plus d times 2, this is a 2, equals 0. Oh, I did it in pink too. Whatever. We can see here now we have -2dx, then when we distribute we get 2dx, so I'm going to cross out this part of this term and then cross out this whole term. And we get -2x here and a positive 2x on the bottom, so I'm also going to cancel these out. Now we can combine these into an equation with all of them. So as far as y's go, we have 2dy plus 4y. So we can factor out the differential operators. We can get 2d plus 4y. And now looking at the z's, we have a -2z here, positive 2dz, and then another positive 2dz. So we're going to have 4dz minus 2, or 4dz minus 2z. And so we can factor out the differential operators and just the coefficient of z once again. We will get 4d minus 2z. And this doesn't equal 0. This equals, we multiplied through by 2, so this will equal 2 times e to the t. And this shows that once we combine all of these terms, we're going to, the -2z will cancel with the positive 2z, and it's going to equal 0. So this is a useful equation. Now we have y in terms of z. Now the goal is, I'm going to take the third equation, this one, x plus 2y plus dz equals e to the t, and we are going to make our equation for y, or make our equation for z in terms of y, have everything in front of the z, all the coefficients in front of the z, look like all the coefficients in front of this z, which is just a d, so we're going to also be multiplying through by operators and constants on this side, or in this equation, and then do the same thing with this equation that we got from the beginning. Negative 2d squared x plus dx plus d plus 2y equals negative e to the t. And so I'm putting this here so I can see it, and I'm rewriting this too. So x plus 2y plus dz equals e to the t. Next step is let's first multiply I'm also going to write the other two equations. And then our last one, I know I could factor out 2 from all of these, but I'm going to leave it as it is. And now I'm going to multiply this first equation through by the coefficient in front of this x, because we're going to be plugging in, we're going to make everything in front of this x be able to fit in front of this x. So in this equation, we need to multiply it through by negative 2d squared plus d. So black means I'm dealing with that first equation. And there's no operator in front, so we just leave it as x. And so we have a 2 in front of the y, so I'm going to factor that out. And a d in front of the z. And then for simplicity's sake, I'm going to do some simplification. Well, that's pretty redundant, but it is what it is. This is negative 4d squared distribution, negative 4d squared plus 2d times x, and, or operating on x, that is, because these are differential operators, it's not multiplication. And finally, doing the last, sorry, this is y. That's a y, and this last is a z. Plus, now we're going to have negative 2d cubed plus d squared z equals, okay, now negative 2 times e to the t plus e to the t is just negative e to the t. Great, our x matches up. Now we could theoretically plug this in. However, we'd still have something with y's and z's, and then we'd have to do even more math to eliminate it with lining up this equation. I'm just going to do it all in one fell swoop. And now I'm going to examine this equation. I'm going to check what's in front of the y. We have 2d plus 4. And I notice we have negative 4d squared plus 2d in front of this y. So there's a disconnect. We are going to multiply the equation with this, the black equation on the bottom. We're going to multiply that through by, well, okay, I am going to simplify this. I'm going to factor out a 2 on all of them. I said I wasn't going to, but I am going to. So if you factor out a 2 of each of these, you can factor out a 2 of everything here, factor out a 2 of everything here, factor that out of both of them, divide through because we have 0 on the other side. So we can turn this into d plus 2, y plus 2d minus 1, z equals 0. And So now we can see in front of the y, we're going to have a d plus 2, which means I want to multiply this equation through that I have on the bottom by d plus 2. So what's that going to look like? It's going to look like this. D plus 2. This is the nastiest part of the problem. So once we're through with this, it's relatively smooth sailing. That's negative e to the t. Space purposes. Now I'm actually going to leave some of these unfactored because we're just going to be replacing our z and our x with something, and with this part of the equation. And now we can see we're getting closer, but we still have, sorry, this equation, a d plus 2 in front of this. We still hold on, I'm just checking with my notes to make sure I got this right. Okay. Lining this, so this, now in front of x we have d plus 2 times negative 2d squared plus dx, and in front of this x we have negative 2d squared plus d, so we're going to need to multiply this equation through by d plus 2, so. And then I'm going to do the same thing with my equation with, so I have this equation with y and z, and we're going to be replacing z with something in terms of y. So I notice here that if we factor out a d squared from these two, it's negative 2d minus, if we factor out a negative d squared, this is going to be 2d minus 1. So there's a negative 2d and a d plus 2. There's already a 2d minus 1 in front of this z. So as far as that goes, we're going to need to multiply this blue equation through by negative d squared and also through by d plus 2. So when we do this, we get d plus 2 squared, because there's already a d plus 2. And we're going to have a negative d squared y plus, we're going to end up with something that looks exactly like this, so I'm just going to write that. D plus 2 times negative 2d cubed plus d squared z equals 0. And we can operate on 0. We're still going to get 0. So next is to isolate just everything in front of the z. So for that, it's going to look like this. We're basically going to add d squared times d plus 2 all squared y, because there's a negative sign here. And when we do that math, we're going to get something that looks like this. D plus 2 times negative 2d cubed plus d squared z equals, on the other side, it will be d squared, d plus 2 squared y. Now is the time. Now we can start to plug in our equations. We're going to be plugging into this black one. It has in front of, before we do that, I'm going to rewrite this orange one with just the x on one side and the y and everything else on the other side. So taking this part, d plus 2, negative 2d squared plus d times x. Then I'm subtracting d plus 2 squared y, which, and when we do d plus 2t e to the negative t, we actually get, so derivative of negative e to the t is negative e to the t, 2 times that. So we're going to get negative 3e to the t on this side. So I'm going to write negative 3e to the t. And we're subtracting d plus 2 all squared y. And so when we do that, we're going to be adding I'm going to factor this out, which would be d squared plus 4d plus 4, but it's negative in front of all of them, so it's going to be negative d squared minus 4d minus 4y. And now we can look here and start matching up terms. So I'm going to underline what's going to be replaced first. So we're going to replace this, underline it in orange because that's what I'm replacing it with negative 3e to the t plus negative d squared minus 4d minus 4y. Next, I'm going to replace this in front of the z, d plus 2 times negative 2d cubed plus d squared z. This part with this. Oh, actually, before I do that, why don't I read it in order? I'm going to just leave what we have in front of y. So plus d plus 2, negative 4d squared plus 2dy. Now I'm going to put this part in. And I'm going to go down to the next line. It's a lot of stuff. Negative 2d cubed plus d squared. This is z. Sorry. We're replacing what's in front of the z. We're replacing that. Sorry, that's just copying. We're replacing it with this. D squared, d plus 2 all squared, y. In the end, and what we have on the other side of the equal sign is d plus 2 negative e to the t. We calculated this one, d plus 2 times negative e to the t, to just be negative 3e to the t. So I'm going to drop that down. And we'll notice these cancel. And now we can start to expand this. So I'm going to write, I'm going to still keep them separated. I'm going to start writing it in green because it's a new equation. And then I'll combine them all into one big operator in front of y. So first one, already factored. Negative d squared minus 4d minus 4y. Second one, when we do this factoring, just going to do some FOIL quick in my head. We'll get negative 4d cubed. And then for our d squared term, this is negative 8d squared. This is 2d squared, so we're going to have negative 6d squared. Finally, for our last term, it's going to be just 2 times 2d, which is 4d. And when I factor this out, I get the d squared plus 4d plus 4, all times d squared. When I do that, every term's going to have, it's going to be just the normal polynomial. It's going to be the normal expansion, but with a d squared multiplying in front of each term. So it'll be d to the 4th plus 4d third to the third plus 4d squared y. And this all equals 0. I'm going to combine now. I'm going to write it in, starting in the highest power. That is the d to the fourth. D to the fourth. I'll cross that in this color. D to the fourth plus 4d cubed minus 4d cubed minus d squared minus 6d squared plus 4d squared. Now for the d's, negative 4d, positive 4d. Now for d to the 0 power, negative 4. All operating on y, all equals 0. Combine, just crossing out what cancels. These cancel. These cancel. We're left with d to the fourth, so negative 7 plus 4 d squared will be negative 3d squared plus, or minus 4 y equals 0. This is great. We can use our method to find the complementary solution. So I'll write the auxiliary equation off to the side. It is m to the fourth minus 3m squared minus 4 equals 0. So we can treat this kind of like we're factoring a quadratic, but instead of it being of order an m squared minus 3m minus 4, the m's are just squared. So we'll factor it out like this. M squared minus 4, and then m squared plus 1 equals 0. Expanding further, m minus 2, m plus 2, this is still m squared plus 1 equals 0. Moving on. When we solve for m, we're going to get m equals 2 in order. So this will get m equals 2. This will give us m equals negative 2. Finally, we'll get m equals positive negative I, square root of negative 1. What this means is our alpha is 0, our beta is 1, which gives us c1 times 1x, so c1 cosine of 1x, so c1 cosine x plus c2 sine x. However, we're not going to be using c1, c2, c3 because we've already used up through c6. I'm going to write the complementary solution, which is just a solution, so I'm just going to write it as y equals, then I'm going to have, we start at c7 cosine t plus c8 sine of t, excuse me, plus c9 e to the negative 2t plus c10 e to the 2t. So if you've been counting coefficients, so to speak, we'll notice in the original problem we're first order in x, highest it gets is just d operating on it. First order in y, highest it gets is d, and first order in z, we get one constant for each letter essentially. So we get 3 coefficients, and since we're at c10, we have 10, which means we're going to have to eliminate 7 of these or find them in relationship to others. I'm going to start by writing out each equation and giving it, and also writing out its first derivative, because each equation and all of its derivatives, we're going to be plugging into those original 3 equations that we got. And it's nice to just have a reference sheet with all of them. I'll start with x. X equals c4 cosine of t plus c5 sine of t plus c6 e to the 2t. What this means is when we take the derivative of this, we're going to get x prime equals negative c4 sine plus c5 cosine plus 2c6 e to the 2t. Now it's time for the y's, which we just solved up here. Still writing it again just so it's in one spot. Lastly, I forgot to differentiate y prime. So we're going to get a negative c7 sine of t plus c8 cosine of t minus 2c9 e to the negative 2t plus 2c10 e to the 2t. Finally, let's get down our z. Z equals, we got c1 cosine of t plus c2 sine of t plus c3 e to the 2t. Same form as x, just we get different constants. Z prime, therefore, it's going to be c1 sine of t plus c2 cosine of t plus 2c3 e to the 2t. This is an important one, so I'll put it up here for now, but I'm gonna try to keep it in the shot for the rest of this video, because that is the remainder of our work. The first equation that I'm gonna plug into is the second one, which is, put it down here, d minus 1 x plus dy plus dz equals 0. To make this more accessible, I'm going to expand it in terms of the notation I used over here. So we're going to get x prime minus x plus y prime plus z prime equals 0. This makes things a little easier to plug in. First, I'm going to plug in, so I'm actually not going to write everything out. I'm going to rewrite it, but I'm going to be grouping in terms of sine, cosine. I'm going to be rewriting it in terms of what's a coefficient of sine, what's a coefficient of cosine, what's a coefficient of e to the 2t, and finally, what is a coefficient of, and I forgot one thing. Our x has a particular solution of e to the t, and that, where did we do that? We did that for the second equation. Yeah, so plus e to the t. When we take the derivative of this, we get e to the t. And we'll see why that's important later. It is important, though. All right. I will start with all of the terms that'll have cosine. So if we go through here, what term in x prime has cosine? Well, it'll be c5. So I'm going to start with the parentheses, c5. Negative x, what term of negative x has a cosine? Well, when we multiply x through by negative 1, we get negative c4 cosine t. So I'm going to do minus c4. Y prime, for their cosine, it's c8. And then for the z, for this, sorry about that, delay, I was checking my notes one more time. For the z prime term, the cosine has a c2 in front of it. And so these are everything, this is everything in front of cosine. Now I will do the same for sine, starting with x prime. Our x prime sine term is negative c4. Our negative x sine term is c5. If we look in y prime, it's going to be negative c7. Oh, sorry, for this x, it is a negative x. So it's going to be negative c4 minus c5 minus c7. And the z prime sine is a negative c1. Now I'm going to look for everything with e to the 2t. For this, we'll start with x prime again, plus, and the x prime, e to the 2t is 2c6. The negative x is going to be negative c6. Our y prime is, we're looking for e to the positive 2t, so this is plus 2c10. And the z prime has a plus 2c3. So we have some oddballs, which would be these e to the t terms that we haven't accounted for, and this e to the negative 2c9 e to the negative 2t, or c9 e to the negative 2t, this term. And because we're only looking at y primes, it's going to be this second one, the negative 2c9 e to the negative 2t. I will do that one first. It's the only one with that coefficient, so I'm going to write plus negative 2c9 e to the negative 2t. And then the last ones are the e to the t terms. So we have an x prime e to the t minus x, which is also going to be e to the t. So e to the t minus e to the t, and it equals 0. The main equation we get from this is, so we do get these relationships with C4, C5, C8, and C2. That's tough because we need a lot. We can't really eliminate many. We can eliminate one variable each from these, but we're still left with one in terms of another 3, and they're a different 3. Because if I had found this in terms of C8, we'd have it in terms of C4, C5, and C2. If I did this in terms of C7, we'd have it in 4, 5, and 1. So even with that, we still have our C3, and so I'm not going to deal with these because these are too hard to deal with for us. However, this will get us so 2c minus c6, that's c6, and plus 2c10 plus 2c3, and this is in front of e to the t. Notice there's no e to the t term on this side, which means the coefficient of the e to the t term, it's invisible, it has a 0 in front of it. I'm going to rewrite this like this, c6 plus 2c10 plus 2c3 equals 0. This is important. We can write c10 in terms of c3 and c6, or c6 in terms of c10 and c3, and that's great because then once we have either c10 or c6, we can have once we have that in terms of c3, then we've eliminated one of those variables. This is where it gets interesting. There's no e to the negative 2t term, so the coefficient negative 2c9 must equal 0, which shows us that c9 equals 0. From there, we can eliminate these terms from y because the coefficient in front of them is 0. And I will strike these through for us so we don't worry about them anymore. The next equation that I'm going to plug into is, so the next equation I'm going to plug into is the x. I'll just write it out. X plus 2y plus dz e equals e to the t. And I'm going to do the same method I did here. This time I have to be careful. Every time I add something with a y, just have to put a coefficient of 2 in front of it. But I'm going to be doing this. I'm going to be going through in the same manner. I'll start with cosine again. Our cosine terms are, for x, c4, or cosine coefficients, I should say. For y, it's c7. Remember, we're multiplying by 2, so we're going to get plus 2 c7. And dz, z prime. Oh, let me rewrite that. Rewrite it in terms of what we're a little more familiar with. X plus 2y plus z prime equals e to the t. Just it's a little easier to see now. Z prime's term is... Ooh, did I knock my video? It's just shaking. Okay. Z prime's e to the t, or z prime's cosine of t is c2. So those are all in front of cosine. Same thing for sine. C5. Plus 2c8. Minus c1. Lastly, that e to the 2t term. For our x, it is c6. 2y, it is 2c10. 2c10. For the z prime, it will be 2c3. And we have an x of e to the t, and we have an e to the t here, and it's all set equal to e to the t, so these cancel. You'll notice this, c6 plus 2c10 plus 2c3, we got this up here. It's expected, there's going to be a little overlap. We are plugging into the same equations after all. So I'm going to just say that I'm not going to worry about this. We already have it written down here. I'm going to write c4 plus 2c7 plus c2 equals 0, since there is no cosine term here. Same thing with sine. c5 plus 2c8 minus c1 equals 0. Now we have a few equations. We still can't get anywhere with these, if you notice. Let's say, yeah, we can replace, this is a C2, sorry. We can try to use some of those long, if we even try to plug into, let's say, C5 minus C4 plus C8 plus C2, we could take C8, isolate it in terms of C5 and C1. Then when we put that in, the C5 matches, but then we're adding a C1, so we don't eliminate a variable. And it's kind of like that for all of them, which is why I'm not dealing with these equations with 4 constants. I'm just going to try to work with 3, and when you'll see when we plug into the last equation, we can actually get some with just 2, which make it really easy. 1 equal to the negative of the other, 1 equal to negative 2 times the other, something like that. And I'm going to put this off to the side so we can still see our main equations. I will now put the last one down. This one is d times x plus z equals e to the t. Sorry, this is d operating on x. Same thing as x prime plus z equals e to the t. We only have to worry about x prime and z. Only these two. When I plug in for cosine, it's C5. For Z, it is C1. And that's in front of cosine. For sine, we have negative C4 in terms of, and then for in front of the Z, we have C1, or what am I saying? C2. Finally, for e to the 2t in that x prime, it's 2c6. And then finally, for that z, it is c3. And we do have a plus e to the 2t on the x prime right there, or plus e to the t. And then this whole thing equals e to the t because of this e to the t. So notice these cross out, which is nice. Now, these are some really, really nice relationships. We'll get C5 plus C1 equals 0. That's nice. We can say, so I'm going to put everything in terms of C1, C2, and C3 because we only get 3 variables, and those are the first 3. It's just kind of nice. So I'm going to say C5 equals negative C1 after subtracting from both sides. That's looking over here. Now I'm going to look over here. Negative C4, oh, and we can set these equal to 0 because there's no cosine term on the other side. Same thing that I'm going to do with sine and e to the 2t. So now I'm going to have C4 plus C2 equals 0. Add C4 to both sides. Flipping around, we can see that C4 equals C2. This is great news. I'm going to do the same thing here. 2C6 plus C3 equals 0. Subtract C3, 2C6 equals negative C3. Divide through by 2. C6 equals negative 1 over 2 C3. We have just eliminated, we've found C5, C4, and C6. We've eliminated 3, and we already eliminated that C9 over here. So we've eliminated 4, and we had 10, so we still need to eliminate 3 more, but we're halfway there. And we can plug in this information that we've just gotten. C5 equals negative C1, C4 equals C2, C6 equals negative 1/2 C3. We can plug those into these 3 variable ones that we had over here to get other relationships. I'm going to say that I'm going to use this one, C6 plus 2C10 plus 2C3, but we know C6 is negative 1/2 C3, so negative 1 over 2 C3, and we're going to be solving for C10, and then, so I'm going to leave C10 and leave 2C3. Just plugged C6, negative 1/2 C3, right in there. Put it down here. I put it down here so we can see it. So 2 is the same thing as 4 over 2. So 4 over 2 minus 1 over 2 is 3 over 2. 3 over 2 C3 plus 2 C10 equals 0. I'm going to subtract the C3 term. We get 2 C10 equals negative 3 over 2 C3. Divide through by 2. C10 equals negative 3 over 4 C3. Great. Let's do the same thing with the C4, 2C7, and C2. We have C4 equals C2. So, how did I write this? Yeah, I can just write a C2 plus 2C7 plus C2 equals 0. I just put C2 in for C4. So I'm going to get 2C2, and then I'm going to subtract by 2C7 on both sides. It's negative 2C7. And then C2, therefore, equals negative, oh, sorry. We want C7 in terms of C2. So I'm going to say C7 equals negative, C7 equals negative C2. C7 equals negative C2. That, when we plug that in, it all goes to 0 if we plug it in here, which is what we're going for. Finally, C1, we have C5 equals negative C1. And we had this equation, and so C5 plus 2C8 minus C1. So minus C1 is the same thing as C5, so C5 plus 2C8 plus C5 equals 0. Now 2C5 equals negative 2C8, and, sorry, I'm going to actually say 2C8 equals negative 2C5. Negative 2C5 is the same thing as, and actually divide to cancel these 2's first. And I have C8 equals negative C5. Negative C5, if we multiply negative 1 on each side of this equation, we're going to get C5, negative C5 equals C1. Or you can plug in negative C1 in for C5. Either way, we get C8 equals C1. I have my relationships all on this page, so I'm going to leave it off to the side. But now we can plug into our equation for x, y, and z, and we'll have our final answer at the end. So x equals C4 cosine t. Over here, C4, we found it equals C2. Great. C2 cosine of t. C5 plus C5 sine of t. We found C5 equals negative C1 minus C1 sine of t. C6. We found that C6 is negative 1 over 2 C3 right here. Minus 1 over 2 C3 e to the 2t. No coefficient in front of this part, the e to the t, so I leave it. Let's move to y's. Y equals, so C7, what do we get for C7? Ah, C7, negative C2. Negative C2 cosine of t. Well, what did we get for C8? C8, we got C1 right here. C8 equals C1 plus C1 sine of t. We eliminated the C9. What do we get for C10? Well, we got negative 3 over 4 C3. Negative 3 over 4 C3 e to the 2t. There was no non-homogeneous part, so that's what we get for y. Let's do z now. Z equals, well, we can just use C1, C2, and C3. They're already in there. Plus C2 sine of t 3 plus C3 e to the 2t. You can plug these into Desmos. You can plug these into your calculator. You can manually differentiate each of them and plug them into the original 3 equations, and it's going to check out. This problem's super difficult. I really liked solving it. It was a blast. I hope you liked solving it too. Thanks for watching.